announcement. We have launched a course called Test Series Plus, where we are providing you with India's largest test series along with the GATE question bank, and it is offered to you at a discounted price of 20%. I think now it is clear, yeah. Good evening, very good evening Saundarya, very good evening Hari, very good evening Sharma ji. Let's move ahead with this. So I was discussing about this Test Series Plus. So it is offered to you at a discounted price of 20%, and now I think audio video is clear now? Yeah, it's fine, yeah, fine. Chalo, let's move ahead with this. So I would like to first tell you what do you mean by stress. Don't confuse yourself. We will going to quickly see the things and we will move to the numericals. Stress is basically the internal resisting force per unit area. So stress is the internal resisting force per unit area is the stress. Now sir, depending on the type of area, these stresses are of two types. First one is the engineering stress. The first type of stress is called as the engineering stress. So engineering stress is defined as the internal resisting force per unit original area. So engineering stress is defined as internal resisting force per unit original area. The other type of stress is called as true stress or actual stress. True stress or actual stress is defined as the internal resisting force. True stress or actual stress is defined as the internal resisting force per unit actual area. On the same note, we have defined strain. So strain is defined as the change in length per unit length. Strain is defined as the change in length per unit length. Now based on which length you are using, again these strains are of two types. First one is called as the engineering strain. So if you are using the original length, then it is called as engineering strain. So engineering strain epsilon naught is equal to delta L upon L naught. Change in length per unit original length is the engineering strain. Then you have true strain or actual strain. True strain or actual strain is equal to change in length per unit actual length. Now my dear, there is one more expression for calculating this actual strain. So actual strain is nothing but natural log of LA by L naught. It is nothing but natural log of LA by L naught, and there is one relation between actual stress and your engineering stress. So actual stress is equal to engineering stress into 1 plus minus epsilon naught. Just keep the focus on the board and you can expect a very easy question in the examination just by observing the board. Please try this question. This is the first GATE question I am coming up with, and I'll just give you 1 minute of time. Use your calculator and please tell me the answer. Use the calculator and please tell me the answer for this. Question says that the engineering strain of a mild steel sample is recorded as 0.1%. The true strain is. Please comment your answers, keep commenting your answers and stay motivated throughout the session by commenting your answers. Please go for it. Please go for it. Please go for it. I'm telling you, just stay with me till last of the session. Today I came up with those areas in which you will definitely commit a silly mistake, or those areas which are very critical to analyze. We will be seeing all those things today itself. Please give me the answer for this question quickly. The question is saying engineering strain of a mild steel sample is recorded as 0.1%. The true strain is, without any confusion, you know just one relation, that actual strain is equal to natural log of LA by L naught. What is actual strain? Actual strain is natural log of LA by L naught. Natural log of LA by L naught. Those people who are finding it difficult to visualize, let me draw this diagram for you. For example, this is a bar. This bar is subjected to an axial load of P. This bar is subjected to an axial load of P, right? The initial length of the bar is L naught. The initial length of the bar is L naught, and under the action of this load, this bar will undergo elongation. So after elongation, the length of the bar become LA. After elongation, the length of the bar will become LA. Now what is change in length? So change in length delta L is equal to LA minus L naught. So sir, can I write down actual length? Actual length is nothing but original length plus delta L. Sir, LA can be written as L naught plus delta L. Just substitute in this expression. So you have actual strain is equal to natural log of L naught plus delta L divided by L naught. Just separate the terms and you will realize that your actual strain is nothing but natural log of 1 plus delta L by L naught. And sir, delta L by L naught is nothing but your engineering strain. It is nothing but your engineering strain. So I will write down epsilon actual is equal to natural log of 1 plus epsilon naught. Substitute the values. So you have actual strain is equal to natural log of 1 plus. Engineering strain is given to you as 0.1%. Don't directly substitute the value. Please keep your eyes open. This is 0.1%. So 0.1% will be written as 0.001. Substitute and get me the answer of actual strain. Please tell me the answer of actual strain. It is natural log of 1.001. Please tell me this answer for actual strain. Please tell me this answer for actual strain. So Saundarya is saying option C. All of you just quickly reply on this. What is this value? What is this value? Actual strain is how much? Please quickly tell me this value. Please quickly tell me this value. This is how much? This is 0.009. Is this the value? Or 0.099? Just tell me this. 0.099. Is this the value? Is this the value? 0.099. Just quickly tell me this. What is natural log of 1.001? Please tell me the value of natural log of 1.001. Natural log of 1.001. Natural log of 1.001 will be 0.00099. 0.00099. 0.00099. Right. So this is nothing but 0.099%. This is the value of your actual strain. I am telling you, directly use the formula. Very good, Piyush. Very good. 0.00099, and in percentage it will be 0.099%. Okay. So this is how you need to approach this. Let's try this next question. Please try this. Have 1 minute of time. Go for it. Please try this question. Quickly, without, like, these are some of the areas where you can commit silly mistakes. So no silly mistakes required. Please go for it. Please go for it. Please go for it. The value of true strain produced in the compressing a cylinder to half of its original length is. It's a very simple question, but most of the student, they commit a mistake here. Do it. Please do this. Please do this. What they are asking, the value of true strain produced in compressing a cylinder to half of its original length is. Let me draw this. Let me draw one cylinder in front of you. So this was a cylinder. This cylinder was subjected to compressive load like this. This cylinder was subjected to compressive load like this, right? Initially, the length of the cylinder is L naught. Say L. Initially, the length of the cylinder is L. Now, after applying the compressive load, this cylinder has reduced to half of its length. Means this is how the cylinder will reduce to half of its length. Now, what is the new length of the cylinder? It is nothing but L by 2. So, original length is L and your actual length is L by 2. Very good, Saundarya, very good, correct answer, absolutely correct answer. So your original length is L and your actual length is L by 2. So you have to simply use the expression actual strain or true strain is natural log of LA by L naught, LA by L naught. Actual strain is natural log of LA by L naught. So this is equal to natural log of L by 2 divided by L. That is why intentionally I have kept this question, because still some of you might think ki sir, the actual strain will be minus 0.5. It's an incorrect answer. That is why I have kept this question. Just give me the value of this. What is natural log of 1 by 2? What is natural log of 1 by 2? And I see there is one correct answer which is saying the natural log of 1 by 2 is minus 0.69. So this is minus 0.69 is your actual strain. Don't make this kind of mistake, I'm telling you. Please keep a check on these easy question. It was a 1 mark question in 2016 for mechanical engineering. It's a very important question. Chalo, let's move ahead with this. This is the next question. This is the next question. This is the next question. Please try it. It's a very easy question, but still it is a very basic question to give you an idea. I am giving you just 1 minute of time because we have to see a lot of concepts today. Go for it. Go for it quickly. Use the short trick. I don't want complete statement, just I want the answers. Go for it. And keep commenting in the comment box. Let me see your heat. Let me see your intent. Keep commenting in the comment box. Keep commenting in the comment box. Go for it. Go for it. Go for it. Please go for it. These questions are just like 1 minute question. We should not take even more than 1 minute to solve these type of questions. Let's see this. Question says that a hanger is made up of 2 bars of different sizes. Each bar has a square cross section. Which type of cross section? Square cross section. The hanger is loaded by 3-point loads in the mid-vertical plane as shown in the figure. Intentionally they are writing all this. Intentionally, in order to confuse you. They could have directly given you the figure and they could have directly asked you find out the maximum stress developed in the body. But intentionally they are framing this kind of picture so that half your mind will be distracted. Let's see this. So what they are saying is, ignoring the self-weight of the hanger, what is the maximum tensile stress in Newton per meter square anywhere in the hanger without considering the stress concentration effects? So here you have a hanger which in this length and this length of the member is there. But we are worried about the cross-sectional area because they are asking you the stress. Very good, Piyush. Very good, Saundarya. Absolutely correct answer. So what you need to do is, say this is your hanger. This hanger is having a cross-sectional area of 100 by 100. It's a square cross-section. And this hanger, this part of the hanger is having a cross-sectional area of 50 by 50. And here you have a load of 50 kilonewtons. So what you need to do every time in the class, I have told you that whenever these type of questions will come, please draw the free body diagram. It will give you the idea. So let me just name this. So this is a hanger. This is a hanger like this. It is a hanger like this. This is a big part and this is the small part of the hanger. And the area of big part of the hanger is 100 by 100. The size of this hanger is 100 mm. This size of the hanger is 100 mm. And this size of the hanger is how much? It is, I think, 50 mm. The size of lower hanger is 50 mm. Okay, sir. This is 50 mm. Now this hanger is subjected to 3 loads. So this hanger is subjected to 50 kilonewton here and 100 on the either side. So I will apply a 50 kilonewton load here. This is 50 kilonewton and 100 kilonewton load on either side. This is 100 and this is also 100. Actually, the analogy of drawing the free body diagram is very important, because if you can understand that analogy, this becomes very simple. So let me name this. This is A, B and C. First, let me take this portion BC and draw the free body diagram of this portion BC. So this is my portion BC. Check this out. This portion BC is subjected to a downward load of 50 kilonewton like this. It is subjected to a 50 kilonewton load downward. But if I draw only this 50 kilonewton load, do you think this will be in the state of equilibrium? No, it will start undergoing rigid body translation. So somebody has to hold it back. So portion AB will apply equal and opposite 50 kilonewton load over this portion BC in order to keep this portion BC in equilibrium. So the total amount of axial load that this member BC is subjected to is 50 kilonewton. The cross-sectional area of this portion BC is 50 by 50. This is the cross-sectional area, and the cross-sectional area of this portion BC is equal to 50 by 50 mm square, because it is a rectangular section, sir. Okay, now what is the stress on portion BC? Stress on portion BC is the axial load on portion BC, which is 50 kilonewton. So 50 into 10 raised to power 3 upon 50 into 50. Please calculate this. And this will come out in Newton per mm square. I have converted this kilonewton into newtons, and this is in mm square, right? So I think this will come out as 20 mm square. Just check this, the answer. 20 Newton per mm square will be the axial stress on this portion BC. Yes. Yes, sir is saying 24, 25. Yeah, absolutely correct. Absolutely correct, sir. So stress in the portion BC is 20 kilonewton per mm square. Now coming to this portion AB, most of the students, they start thinking, sir, why we should draw the free body diagram? What is the importance of this free body diagram? So let me show you the importance. This 50 kilonewton load is applied by portion AB on portion BC to hold it back. In reaction to this 50 kilonewton load, portion BC will also apply equal and opposite 50 kilonewton load like this. And externally 200 kilonewton loads are acting on the either side of this portion AB. So in total, portion AB is subjected to 250 kilonewton of load. Portion AB is subjected to 250 kilonewton load, and equal and opposite 250 kilonewton of reaction will be provided by the support. So this is your portion AB. Now what you need to do is, for calculating the axial stress on this portion AB, you have to simply take the stress and divide with the area. So stress on the portion AB is equal to the total load on portion AB, which is 250 into 10 raised to power 3 Newton, divided by area of this portion, which is 100 into 100. So I think this will come out as 25 Newton per mm square. So you can check it out that portion AB is subjected to maximum tensile stress, and the value of this stress is 25 megapascal. Why I have considered this question? In order to draw this basic free body diagram to give you an idea. Who will apply this 50 kilonewton load? Portion AB will apply on portion BC in order to hold it back. Who will apply this 50 kilonewton load? In reaction to this 50, BC will apply equal and opposite 50 over this portion AB. So this is the question, very basic question. Let's move ahead with this. Let's try the next question. Okay, before attempting the next question, first understand this. Let me just quickly give you a brief about the Hooke's law. Let me just quickly give you a brief about the Hooke's law. What does Hooke's law states that? Most of the student will answer one very simple thing. The moment Hooke's law comes to their mind, they simply answer this: stress is directly proportional to strain. That's all. Nothing ahead of this. So I am here to tell you that we have three different types of Hooke's law. First one for axial loading. So Hooke's law for axial loading states that that axial stress is equal to Young's modulus into axial strain. Axial stress is equals to Young's modulus into axial strain. Second one is Hooke's law for shear loading. Hooke's law for shear loading states that shear stress is G into phi, where G is the modulus of rigidity and phi is the shear strain. And third one is Hooke's law for hydrostatic loading. Hooke's law for hydrostatic loading. Hooke's law for hydrostatic loading. What is Hooke's law for hydrostatic loading? Hooke's law for hydrostatic loading states that loading states that your change in pressure, negative of change in pressure, is equal to bulk modulus into volumetric strain. Minus delta P is equals to K into epsilon V. These are the three different Hooke's law, and here we have seen three different elastic constants, E, G and K. E is the Young's modulus, G is the shear modulus and K is the bulk modulus. Apart from this, we have one more thing which is termed as the Poisson's ratio. We have one more constant which is termed as the Poisson's ratio. We have one more constant which is termed as the Poisson's ratio. We have one more constant which is termed as the Poisson's ratio. Now sir, what is Poisson's ratio? Poisson's ratio is defined as minus of lateral strain to longitudinal strain. Minus of lateral strain to longitudinal strain. Minus of lateral strain to longitudinal strain. Longitudinal strain. Minus of lateral strain to longitudinal strain. E, G, K and mu are the properties of the material. It will only change if you will change the material. If you are not changing the material, then these values will not going to change. On the same note, I will say E, G, K and mu are also termed as elastic constants. These are termed as elastic constants. What are these termed as? They are termed as elastic constants, and we have four different relations for these elastic constants which should be known to every engineering aspirant for civil and mechanical who will be appearing in the GATE exam, especially for those students who will be taking up XC exam considering strength of material as a subject. So E, G, K and mu are termed as the elastic constants. These are the properties of the material which will only change if you will change the material. Like Young's modulus of steel will be different from the Young's modulus of aluminium, will be different from the Young's modulus of copper, will be different from the Young's modulus of wood. Like that you have these elastic constant. Now what is the first relation between elastic constant? The first relation is E is equals to 3K into 1 minus 2 mu. What is first one? E is equals to 3K into 1 minus 2 mu. What is the second one? Second one says that E is equals to 2G. E is equals to 2G, just like what is before 3G, 2G. So E is equals to 2G into 1 plus mu. E is equals to 2G upon into 1 plus mu. And the third one is E is equals to 9 kg. E is equals to 9 kg upon 3K plus G. What is the third one? Third one is E is equals to 9 kg upon 3K plus G. All these three elastic constant relations are based on E, right? Fourth one is based on mu. The fourth one states that mu is equals to 3K minus 2G. 3K minus 2G upon 6K plus 2G. 6K plus 2G. Mu is equals to 3K minus 2G upon 6K plus 2G. For isotropic material, the number of independent elastic constants required are 2. For orthotropic material, the number of independent elastic constants required are 9. For anisotropic material or non-isotropic material, the number of independent elastic constants required are 21. So I have given you a table, accordingly you can choose this. But these four relations are very important from the exam point of view because these relations will going to help you in several other ways. Let's try one basic question from this. Please go for it. Just 1 minute of time, go for this question. Just 1 minute of time for you. Please try this question. Please try this question. Just 1 minute of time. Keep answering in the comment box, in the chat box. Keep the chat box ticking. Literally today I am feeling the heat, and that heat is to give you best of the content in just very small time, and the same kind of energy I am expecting. Very good, very good. Keep answering, beta, keep answering. Keep answering. We will going to see half of strength of material today without any problem, without any confusion, and especially the kind of shear force and bending moment diagram I will be drawing today. You will never see in any of your books, neither in any of your notebooks. Go for it. Go for it, go for it. The question says that for a material having modulus of rigidity 100 gigapascal. Sir, modulus of rigidity or shear modulus is given to us. Modulus of rigidity G is equals to 100 gigapascal. The modulus of rigidity G is equals to 100 gigapascal and the Poisson's ratio of the material is 0.5. The value of mu is given to you as 0.25. Sorry, the Poisson's ratio is given to you as 0.25. Calculate the Young's modulus and the bulk modulus. The student, those who don't know the elastic constant, they will feel like what kind of question is this? But my students who know the value of elastic constants, they will just write the equation and quickly calculate the value of these elastic constants, right? So for calculating the Young's modulus, can you tell me what should be the relation that I will be using? For calculating Young's modulus, can anybody quickly comment in the comment box and tell me which relation I should use? For calculating this Young's modulus only. Bulk modulus we will calculate later. For Young's modulus, if G and mu is given to us, which relation I should use? We have written 4 relations. You can just number them 1, 2, 3 and 4. Which relation I should use? First one, second one, third one or fourth one? Quickly tell me. Only for calculating the Young's modulus, which relation I should use? First one, second one, third one or fourth one? Quickly, I am just waiting. I am just waiting for your answers. Quickly tell me which relation I should use. I have the value of G, I have the value of mu and I want the value of Young's modulus. Quickly comment. Let me see how many of you still remember those relations. Quickly comment, quickly comment. So you have to calculate the Young's modulus. Please comment, please comment. Which relation I should use? First, second, third or fourth? First 3 are of Young's modulus and the last one is of Poisson's ratio. Which one I should use? 1, 2, 3 and 4. Please give me your answers. I am waiting for it. Please give me your answers. Very good, very good. We should use the second one. The second relation says that E is equals to 2G into 1 plus mu. So first calculate the Young's modulus. So E is equals to 2 into G. So 2 into 100. 2 into 100 into 1 plus 0.25. Please tell me the value of Young's modulus. Quickly calculate. Very good, Saundarya. Very good. Very good. Very good, Kirti. Very good. Please tell me the answer for this. What is the value of Young's modulus? So E is equals to 2 into 100. E is equals to 2 into 100 into 1 plus 0.25. Please tell me the value of E. It is equal to 250 megapascal. Very good. So E is equals to 250 megapascal. E is equals to 250 gigapascal. Because the value of G is in gigapascal and mu is unitless. Okay. Now you need to calculate the bulk modulus. You can use any of the relation of your choice. But for me the simplest one is E is equals to 3K into 1 minus 2 mu. For me the simplest one is E is equals to 3K into 1 minus 2 mu. E is equals to 250. This is equal to 3 into K into 1 minus 2 into 1 minus 2 into 0.25. Please calculate this. Get me the value of K as well. And all of you keep answering this. All of you please keep answering on this. What will be the value of K here? What will be the value of K? Keep answering, keep answering. Keep your hands and calculator active. The minimum you should write. Minimum you should write and maximum you should calculate. Please do this. Get me the value of K here. Please tell me the value of K. So E is equals to 250. Now calculate K. So this will be how much? This will be 0.5. 1 minus 0.5 will be 0.5. 0.5. So this will be 125. 125 by 3. What is 125 by 3? What is 125 by 3? Please tell me what is 125 by 3? No, this will be 0.5, so this will be 500 by 3. Sorry, 500 by 3. Sorry, 500 by 3, yeah, 500 by 3. 166.67, yeah. The value of K is 166.67. 166.67 gigapascal is the value of K, right? And like this, you can expect a question in your examination regarding use of these elastic constants. But these elastic constants have several other usages as well. So, yeah. 4.15, which one? Ronaldo sir on the channel is saying 4.15. I think he's answering the previous question. The next question says that, which of the following is the definition of the ultimate tensile strength UTS obtained from the stress strain test on a mild steel sample? Chalo, let's quickly see this. What is a mild steel test, right? So you basically take a cylindrical specimen in which the gauge length to gauge diameter ratio is 4. Gauge length is that length over which the elongations are measured using the extensiometer, and this specimen is fixed in the universal tensile testing machine and it is uniformly loaded. Now when you start loading the sample, before that, let me draw this diagram, stress versus strain. Now my simple question is, sir, why stress is on the y-axis and strain is on the x-axis? Because this question can be asked to you in a very different way in many of the interviews. First of all, whichever thing is written in the x-axis, that is an independent parameter or independent variable. The thing which is written on the y-axis is a dependent variable. So why stress is written on the y-axis and strain is written on the x-axis? The answer is very simple. When you apply the load over any body, first this body will undergo deformation. In order to resist the deformation, stresses are induced. Okay, so stresses are always dependent on strain. So what can I have a note point here? The first note point is stress is a dependent variable and strain is an independent variable. So I will simply write down here that stress is the function of strain. Stress is a function of strain. First strain will come, then only stress will come. Now let's quickly see the stress strain diagram for mild steel. So stress strain diagram for mild steel starts like this. So when you initially apply the load, the stress will be directly proportional to strain up to the proportionality limit, and the curve is straight line. The slope of this straight line is nothing but the Young's modulus. The slope of this line is nothing but the Young's modulus. So when you remove the load, the material will going to regain its original shape and size. Beyond point A, the stress and strain variation is non-linear, and then we get this point which is called as the elastic limit B. So this AB portion is non-linear till B. If you remove the load, the material will going to regain its original shape and size. But this portion AB is non-linear. Beyond point B, whatever deformation will come over the bar, that will be permanent deformation. Till point B, whatever deformations are coming over the bar, those are elastic deformations. So whatever strain that comes till point B are termed as elastic strains. The strain coming over the material till point B is termed as elastic strain. So this value of strain is termed as elastic strain. So from O to this point B, this is your elastic strain. This is elastic strain, right? Now beyond point B, whatever deformations will be coming, those deformations will be the permanent deformations or the plastic deformation. So on loading the material beyond point B, you will get the upper yield point C dash and the lower yield point C. This fall in stress from C dash to C takes place at constant value of strain, and this fall in stress is because of the slippage of carbon atom inside the internal structure of mild steel. Now sir, at this constant value of stress, you can see this, at this constant value of stress, the body will undergo huge deformation, which is called as yielding. At the constant value of stress, the body will undergo huge deformation, which is called as yielding. And when the material is undergoing yielding, the reorientation of the internal structure will happen, and you will get a new configuration at this point D, where the yielding ends. This new configuration of mild steel at point D is capable of withstanding more amount of load. That is why on loading the material beyond point D, it will going to offer additional amount of stress. It will going to offer additional amount of resistance. That is why you get a strain hardening zone from D to E. So this is your strain hardening zone. Strain hardening zone. Strain hardening zone from D to E. Strain hardening zone from D to E, right? Then you have the ultimate load point. The value of stress at this ultimate load point is called as ultimate tensile strength of mild steel. The value of stress at this ultimate load point is called as ultimate tensile strength of mild steel. And after this point E, the necking of the material will going to start, and the material will going to fail at this point F, which is called as the fracture point. This is called as the fracture point, and EF is called as the necking zone. This portion EF is called as the necking zone. This portion EF is called as the necking zone. Again, I would like to tell you, the value of stress corresponding to this ultimate load point is called as ultimate tensile strength of mild steel. The value of stress corresponding to this ultimate load point is called as ultimate tensile strength of mild steel, and this ultimate tensile strength of mild steel is defined as the maximum load that can be applied over the mild steel divided by the original cross-sectional area. The ultimate tensile strength of mild steel is equal to maximum applied load, maximum load applied divided by the original cross-sectional area, divided by the original cross-sectional area. Just check the options and tell me which option is the correct option. Which option is the correct option for ultimate tensile strength of mild steel? Check for option A, B, C, D and tell me. Meanwhile, I just read the comment. Yeah, necking zone means the object is ready to get failure. No, beta. Necking zone means that the cross-sectional area is getting reduced and the material is on the verge of shear failure. The material is on the verge of shear failure. Necking zone simply means the reduction in the cross-sectional area. Sir, yield stress, upper and next lower yield limit, ultimate tensile strength, failure area. Very good. Very good, very good. Mr. CR7, can you just type your name as well? Your YouTube handle is Ronaldo channel. So UTS, maximum tensile strength is maximum load applied divided by the original cross-sectional area. Can you tell me which option is correct? A, B, C, D. Option A says that stress value where the stress strain curve transitions from elastic to plastic behavior. The stress value where the stress strain curve transitions from the elastic to plastic behavior. This is your elastic limit. The option A is your elastic limit. This is elastic limit. This is elastic limit where your body will transition from elastic to plastic behavior. The maximum load attained is divided by the original cross-sectional area. No. Then you have the maximum load attained is divided by the corresponding instantaneous cross-section. Okay. The maximum load attained is divided by the original cross-sectional area. Sorry. Too much of heat is there. So this is the correct option. This is the correct option. Ultimate tensile strength is maximum load applied divided by the original cross-sectional area, right? So this is the correct answer for this option. This is the correct option for this question. Let's move ahead with this. I would just like to tell you few things here. The strain up to the elastic limit is called as elastic strain. The value of strain beyond the elastic limit till this fracture point is called as plastic strain. This is plastic strain. Check this out. The value of strain from this elastic limit till this fracture point is called as plastic strain. This is called as plastic strain, right? And the total amount of strain till the fracture point is called as fracture strain. You need to understand the difference. You need to understand this difference, that from point B till point F, whatever value of strain that will come is called as plastic strain, and the total strain till the fracture point is called as fracture strain. From here we define one very beautiful property which is called as ductility. A material is said to be ductile if plastic strain is more than 5%. What I said? A material is said to be ductile if plastic strain is more than 5%. If plastic strain is more than 5%, then the material is said to be ductile. Then the material is said to be ductile. If plastic strain is less than 5%, then the material is brittle. If plastic strain is less than 5%, then the material is said to be brittle material. Now sir, they will not ask you like this. They will not going to ask you the definition. I am telling you one thing. What they will give you is, they will going to give you 3-4 materials, and they will going to give you the value of plastic strains, and they will ask you which one is more ductile, which one is more brittle. So you have to simply observe the value of plastic strain. The material which has more value of plastic strain will be more ductile. The material which has less value of plastic strain will be more brittle. So from here you need to identify which material will be more ductile and which material will be more brittle, right? Very good. Let's see this. Let's move ahead with this. Please try this question. The question says that the symmetry of a stress tensor at a point of the body under equilibrium is obtained from. Just a very easy question. Please go for it. All my classroom students should answer this in just 1 minute, because we have also seen the derivation. Just go for it. All of you just quickly answer this. Absolutely correct, Ronaldo sir. Steel is ductile, cast iron is brittle. But I told you a more fantastic concept, that you have to observe the plastic strain in order to compare ductility and brittleness of the material. Go for it, go for it. The symmetry of a stress tensor at a point in the body under equilibrium is obtained from. Please give the answer. Please give the answer, everyone. Keep typing, yaar, keep typing. Keep typing your answers. We have to see a lot of things. Keep typing quickly, keep typing. Keep typing. Anyone with this answer? I am still waiting for your answer. Very good, Saundarya, very good. Saundarya is saying moment equilibrium equation. Okay. Anything? Moment equilibrium equation. So first one is conservation of mass, force equilibrium equation, moment equilibrium equation, and conservation of energy. Let's see this. First of all, what is stress tensor? Chalo, check this out. Stress tensor. So stress tensor, so for that you need to understand the tensor quantities. First of all, if you want to write down stress tensor, so you need to understand tensor quantities. So you have seen scalar quantities. Scalar quantities have only magnitude. Let me write this. So scalar quantities, the quantities which will have only magnitude are termed as scalar quantities. The second one is the vector quantities. What are vector quantities, sir? The quantities which have a magnitude, along with that which have a direction, which have a magnitude and direction, are termed as vector quantities. Now sir, what is this new thing, tensor? Tensor to we haven't learnt till we attended the class of the sir. The tensor quantities are those quantities which have one magnitude and two directions. What is tensor quantities? Tensor quantities are those quantities which have one magnitude and two directions. Sir, what are these two directions, sir? How can a quantity can have two directions, sir? How it is possible that if I am moving in this direction, I can have other direction also? So for you, tensor quantities are not applicable, right? Tensor quantities are, example of tensor quantities are stress, point number one, strain, third is moment of inertia. What are the three examples of tensor quantities? Stress, strain, and moment of inertia. Now check this out. So a tensor quantity is having magnitude and two direction. For example, if I write down sigma xx. Now sir, what is this first x? This first x is the direction of plane. It is the direction of plane. It is the direction of plane on which this stress is acting. So what is this first x? First x is the direction of plane on which this stress is acting. This second is the direction of force. This is the direction of force. This is the direction of force which causes this stress. This x is the direction of force which causes the stress, and this sigma is nothing but the magnitude. This sigma is nothing but the magnitude. Sir, still I am not getting, sir. I am not understanding why you are writing this sigma as the magnitude. X is the direction of plane and this x is the direction of force which causes this stress. Let me give you an example quickly. We have seen this example a lot of time. Okay, so this is the block I have drawn. This is my x direction. Too much of energy today. This is x direction, this is y direction, and the direction coming out of the board is z direction. X, y, and z. What I said? First represents the direction of plane. Direction of plane is always given by the direction of normal to that plane. So for example, if I have to represent this plane, the direction to the normal to this plane is towards x direction. The direction to this plane is towards x direction. So this will be my x plane. What will be the direction of this plane? This is my x plane because the normal to this plane is along x direction. Okay. So if I apply a normal stress, sir, normal stress, sir, the stress which acts perpendicular to the cross section is the normal stress. So if I apply a normal stress, what is normal stress? The stress which acts perpendicular to the cross section. So this normal stress is acting on which plane? It is acting on x plane. It is acting on which plane? It is acting on x plane. Who will cause this normal stress? If you apply the axial load along x direction, then this normal stress will be caused, and this normal stress is equals to sigma x comma x. This first x represents the direction of plane and the second x represents the direction of force which causes this stress. So I will write down this element is subjected to a normal stress of sigma xx. Similarly, if I draw this stress like this, it is now very easy to answer. This is the normal stress acting on which plane? It is acting on this y plane. Who will cause this normal stress? A force in the y direction will cause this normal stress. Therefore, the name of this normal stress is sigma yy. So this is sigma yy. This is sigma yy. This is the normal stress acting on y plane due to the force in y direction. Okay, sir. If I draw one shear stress, sir, shear stress. Sir, shear stress. By the stress which acts along the surface is the shear stress. This shear stress is acting on which plane? It is again acting on x plane. This shear stress is acting on x plane. Who will cause this shear stress? The force along y direction will cause this shear stress. So I will name this shear stress is tau xy. The name of this shear stress is tau xy. Similarly, if I draw one shear stress like this, so this shear stress is acting on y plane. So this is my tau y. Now who will cause this shear stress? The force along x direction will cause this shear stress. So this is tau yx. Similarly, I will draw like this. This is tau xy and this will be tau yx. All the theory we have seen. Now what they are saying is why this tau xy is equals to tau yx. First of all, these two are termed as complementary shear stresses. Tau xy and tau yx are termed as complementary shear stresses. We have three sets of complementary shear stresses. Okay, that can be shown by drawing the stress tensor. So stress tensor looks like this. Stress tensor looks like this. Stress tensor looks like this. So you have element sigma xx, then you have tau xy, then you have tau xz. Then second will be tau yx, then you have sigma yy, and then you have tau yz. The third will be tau zx, then you have tau zy, and then you have sigma zz. So this is your stress tensor. What we say that this stress tensor is a symmetric matrix. So this stress tensor is a symmetric matrix. It is a symmetric matrix. What it is? It is a symmetric matrix, and it is also a square matrix. It is a square symmetric matrix. So if I am saying square symmetric matrix, means this element should be equal to this element should be equal to this element, and this element should be equal to this element. Since it's a square symmetric matrix, so I will write down tau xy is equal to tau yx, tau xz is equal to tau zx, and I will also write down tau yz is equal to tau zy. All these shear stresses are termed as complementary shear stresses. All these shear stresses are termed as complementary shear stresses. These are complementary shear stresses. Complementary shear stresses. Now, in order to prove this, in order to prove that these values are equal, what I will do is I will simply consider one element like this, and this element is subjected to a shear stress of tau xy and tau yx like this. And on the other plane also, this is tau xy and this is tau yx like this. Okay. Now what I need to do is, about this point, I have to simply write down summation of moment equal to 0. Summation of moment about O equal to 0, and after writing this equation, I can very well prove this, that tau xy is equals to tau yx. Already we have done the proof, so I am not going into the detail. I am just giving you an idea that by the conservation of moment about point O, I can say that these complementary shear stresses will be equal and opposite in direction. Coming back to the question, coming back to this question, what the question says that the symmetry of the stress tensor means tau xy is equals to tau yx, tau xz is equals to tau zx, tau yz is equals to tau zy. This is proven by the moment equilibrium equation. So option C is the correct option here. Option C is the correct option here. It's a 1-mark question asked in the year 2005. Okay, sir. Let's move ahead with this. So we have discussed about the stress tensor, how to write down the stress tensor. That also I have given you an idea. On the same note, I'll just give you an idea about strain tensor. So whenever from stress tensor, always write down stress tensor, always write down stress tensor first, and using the stress tensor write down strain tensor. Always write down stress tensor, and using stress tensor write down strain tensor. So wherever normal stress is coming, replace it with the normal strain. Wherever shear stress is coming, replace it with phi by 2, shear strain by 2. All the details we have read this in the class. I am just giving you a quick idea, right? So if you have to write down strain tensor will be like this. Strain tensor will be like this. Strain tensor is equals to, so you have epsilon xx, then you have phi xy by 2, then you have phi xz by 2, then you have phi yx by 2, and then you have epsilon yy, and then you have phi yz by 2, then you have phi zx by 2, then you have phi zy by 2, and then you have epsilon zz. So this is your strain tensor. Now my dear, the best part is strain tensor is also a square symmetric matrix. This is also a square symmetric matrix. Your strain tensor is also a square symmetric matrix. Square symmetric matrix. It is also a square symmetric matrix. It is also a square symmetric matrix, means your phi xy is equal to phi yx, phi xz is equal to phi zx, your phi yz is also equal to phi zy. It is also a square symmetric matrix. So all these values, this value will be equal to this value, this value will be equal to this value, and this value will be equal to this value. Now using this strain tensor, let's try one question here. Please try this question. Please try this question. 1 minute of time, go for it. Keep commenting your answers. I want answers from all of you. Keep commenting, keep commenting. I have given you 2 minutes, but it is just 1 minute. Go for it. 1 minute for reading, 1 minute for solving. Go for it. Keep commenting. Yeah, Ronaldo sir, you can also keep commenting. All of you just keep commenting your answers. Keep commenting your answers. So question says that assuming E is equals to 160 gigapascal and G is equals to 100 gigapascal for a material, a strain tensor is given as. So this is the strain tensor given to you. The value of shear stress tau xy in megapascal is. So sir, for calculating tau xy, by Hooke's law you can write down, by Hooke's law you can write down shear stress tau xy is equal to G into phi xy. Shear stress tau xy is equals to G into phi xy. Do you know the value of phi xy? Yes sir, this is the value of phi xy. This is phi xy by 2. Actually, phi xy by 2 is 0.004. Phi xy by 2 is 0.004. So what will be the value of phi xy? Phi xy will be equal to 0.008. This is the value of phi xy. Now once you know the value of phi xy, substitute here, you know the value of G. And please remember to keep this value of G in megapascal. So the value of tau xy is equal to G into phi xy. So the value of G is 100 gigapascal. So this can be written as 100 into 10 raised to power 3 megapascal. And the value of phi is 0.008. So this answer will come out in megapascal because the unit of strain, there is no unit for strain. It is a unit-less thing. Give me the value of tau xy quickly. Please tell me the value of tau xy. So this 10 raised to power 3 and this 10 raised to power 3 will cancel out. Minus 3 will cancel out. You have 8 into 100. So I think this will be 800 megapascal. Just check this out. Is it coming out as 800 megapascal? Yeah. So this is 800 megapascal. Okay. Let's move ahead with this. Okay. Before moving ahead in the next question, let me just give you one quickly out brief here that differential form of strains. Differential forms of strain. Differential forms of strain. Now sir, what is differential forms? If U, V and W are the change in coordinates, along x, y and z direction, then normal strain along x direction is equals to del u by del x. Normal strain along y direction is equals to del v by del y. And normal strain along z direction is equal to del W by del Z. This is the normal strain along X, Y and Z direction. Then sir, the shear strain along X direction on the XY plane, shear strain phi XY is equals to del U upon del Y plus del V upon del W. Sorry, del V upon del X. This is shear strain on the XY plane, phi XY. Then shear stress on XZ plane is equal to del U upon del Z plus del W upon del X. Then shear strain on the YZ plane is equal to del V upon del Z plus del W upon del Y. Please remember this. This is the differential form of normal strains and shear strains where X, Y and Z are your directions and U, V and W are the change in coordinate along X, Y and Z direction. So this is your normal strains along X, Y and Z and shear strains on the X, Y and Z. On the same note, for example, if there is an element like this element is subjected to triaxial loading. So let me just quickly give you an example. So I will write down analysis of triaxial loading. Analysis of triaxial loading. Analysis of triaxial loading, right? So we have one element which is subjected to normal stresses along X, Y and Z direction. So this is normal stress along X direction, sigma X. Normal stress along Y direction is sigma Y and normal stress along Z direction is sigma Z. So this is sigma Y and this is also sigma Y and then you have this sigma Z. This is sigma Z. This is normal stress along X, Y and Z direction. So usually which type of question you can expect from here? They will ask you strain along X direction, strain along Y direction, strain along Z direction, or they can even ask you the volumetric strain. So how to write down? First of all, if you have to write down strain along X direction, just observe how much amount of strain this sigma X will cause. So I will write like this, strain along X direction. Strain along X direction, strain along X direction, strain along X direction. So if you have to write down strain along X direction, first of all observe this sigma X. This sigma X will try to elongate the member along X direction. So I will write down strain along X direction epsilon X is equals to sigma X by E, is equal to sigma X by E. But this sigma Y, the Poisson's effect of this sigma Y will try to contract the length of the member along X direction. So I will write down minus Poisson's effect of sigma Y. So minus mu times of sigma Y by E. First, if you are writing strain along X direction, so you have to write down strain due to sigma X. Then you have to consider other two stresses for their Poisson's effect. Like you can see this, if sigma Y is acting in the Y direction, it will try to contract the member along X direction. Similarly, this stress sigma Z acting here will also try to contract the member along X direction. So minus Poisson's effect of sigma Z minus mu times of sigma Z by E. So this is strain along X direction. Similarly, you can write down strain along Y direction. Strain along Y direction. You can write down strain along Y direction. So if you have to write down strain along Y direction, first observe this sigma Y. So this sigma Y will try to elongate the member along Y direction. So I will write down strain along Y direction is equal to sigma Y by E. Then this sigma X which is acting along X, the Poisson's effect of it will try to contract the height of the member. So I will write down minus mu times of sigma Y by E. Minus mu times of sigma X by E, the Poisson's effect of sigma X. Then the Poisson's effect of the sigma Z also will try to contract the height of the member. So I will write down minus mu times of sigma Z by E. Minus mu times of sigma Z by E. So this becomes your strain along Y direction. Now comes to the strain along Z direction. So strain along Z direction is strain along Z direction. Strain along Z direction is, so strain along Z direction epsilon Z is equal to, first you observe this sigma z. So I will write down this will be sigma z by E. Then the Poisson's effect of sigma x. So minus mu times of sigma x by E minus mu times of sigma y by E. Minus mu times of sigma y by E. So this is your strain along x, y and z direction. If you have to find out the volumetric strain, just take the sum of all these strains. So volumetric strain is nothing but epsilon x plus epsilon y plus epsilon z. Volumetric strain is equal to epsilon x plus epsilon y plus epsilon z. Just add all of them and you will get volumetric strain is equal to sigma x plus sigma y plus sigma z, sigma x plus sigma y plus sigma z into 1 minus 2 mu divided by E. This is your volumetric strain. Now from here we came to know two things. If sum of the stresses acting over a body, sum of the normal stresses acting over a body is equal to 0, then volumetric strain is equal to 0. So there are chances that even if the body is incompressible, there will be no volumetric strain if the sum of the normal stresses acting over the body is equal to 0. The second criteria is if the value of Poisson's ratio is equals to 0.5, then the material is said to be incompressible. So if they are saying that the material is incompressible, directly you can consider the value of mu as 0.5. So this is the most complicated case where we have considered normal stress along x, y and z direction. In the question they have given you a very simple case. Chalo, go for it. Have 2 minutes of time, please try this. Have 2 minutes of time and please calculate the value and keep commenting in the comment box your answers, whatever you are getting. If you are understanding or not, please start commenting. Please do this. Chalo, quickly, we will going to see this. The question says that the plate is in equilibrium, is subjected to a uniform stresses along its edges with magnitude of sigma x 30 megapascal, sigma y 50 megapascal as shown in the figure. The Young's modulus of the material is 2 into 10 raised power 11 Newton per meter square and the Poisson's ratio is 0.3 if sigma z is negligibly small and assumed to be 0. So sigma z value is given to you as 0. Then they are asking what is the strain in z direction. So a very simple case is given to you. Let's see this. So this is your stressed out element. For this element, the value of sigma x and sigma y is given to you. The value of sigma x, this is sigma x, and the value of sigma y is given to you. This is sigma y. Okay, and what they are asking to write down strain along z direction. So let's write this. Strain along z direction is strain along z direction. Strain along z direction. So what is strain along z direction? Is there any sigma z? No sigma z. No sigma z. So strain along z direction will directly start from the Poisson's effect of sigma x and sigma y. If sigma x is tensile, it will try to contract the width of the member. So the Poisson's effect of sigma x will be negative. It will be contracting. So I will write down minus mu times of sigma x by E. Then again, the sigma y is also tensile. It will also try to contract the width of the member. So the Poisson's effect of this sigma y will also reduce the width of the member along z direction. You know all the values, substitute and get the answer. So epsilon z is equals to minus mu by E. Inside bracket you have sigma x plus sigma y. Please do the calculation and quickly tell me the answer. So epsilon z will be how much? So mu is 0.3 and E is 2 into 10 raised power 11 Newton per meter square. So I will write down this is minus 0.3 and here I will write down 2 into 10 raised power 5 megapascal. So this will be megapascal, right? Because the sigma x and sigma y is also given to you in megapascal. So sigma x is 30, sigma y is 50. Sigma x is 30 plus 50. And this is also in megapascal. So megapascal and megapascal will cancel out. And we know that strain is unitless. Please tell me the answer for this. Please tell me the answer for this. Saundarya is telling me option number A. Can you please tell me the value for this? What is 0.3 minus 0.3 into 80 divided by 2 into 10 raised to power 5? Please tell me the answer for this. What is epsilon z? Quickly, all of you should answer this. Quickly tell me the answer for this. Please tell me the answer for this. Please tell me the answer for this. Please tell me the answer for this quickly. We have to see a lot of things. Please tell me the answer. This is minus 1.2 into 10 raised to power minus 4. Okay. So minus 1.2 into 10 raised to power minus 4. Minus 1.2 into 10 raised to power minus 4. Yeah, so option A will be the correct option. Minus 120 into 10 raised to power minus 6 will be the correct option. Okay, let's move ahead with this. Okay, this is one of the most fantastic question. Every time I solve this question, I want you people to solve it properly. Okay, here just two things. If you have a biaxial state of loading, if you have a biaxial loading like this, for example, this is your biaxial loading. Sigma x and sigma y is given to you. Sigma x and sigma y is given to you. And you know the value of strain. So what will be the value of strain? Epsilon x. Epsilon x is equals to sigma x upon E minus mu times of sigma y upon E. Similarly, if you have to write down strain along y direction, so this will be sigma y upon E minus mu times of sigma x upon E. If you have to write down sigma x and sigma y in terms of epsilon x and epsilon y, so this can be written as sigma x is equals to E upon 1 minus mu square into epsilon x plus mu times of epsilon y. Similarly, if you have to write down sigma y is equals to E upon 1 minus mu square epsilon y plus mu times of epsilon x. Please remember these formulas, these sets of formulas are very important. Sigma x is equals to E upon 1 minus mu square into epsilon x plus mu times of epsilon y, and sigma y is equals to E upon 1 minus mu square epsilon y plus mu times of epsilon x. Where we have derived these equations? We have derived this from this set of relation. Okay. Now please attempt this question. Okay, if epsilon x and epsilon y needs to be calculated, then you can use the differential. So epsilon x is equals to del u upon del x, and you have epsilon y which is equal to del v upon del y. So I have written all the information which is required to solve the question. One more, tau xy is equals to g into phi xy, and what is the value of phi xy? Phi xy is nothing but del u upon del y plus del v upon del x. Just see how complicated questions could be. Okay, so you have to use all these relations in this previous question. So first have a glance to all these relations, and now please attempt this question. I'll give you proper 2 minutes of time. Please attempt this question, and I want all of you to answer this because all of you have done this question in the class. Please go for it. Please go for it. It's a very fantastic question. Please go for it. Please go for it. Go for it, solve this. Please go for it. Chal, let's see this. Question says that a 2D thin plate with a modulus of elasticity E is equals to 1 Newton per meter square. I'll simply write down all the data. E is equals to 1 Newton per meter square. Okay, sir. E is equals to 1 Newton per meter square, and the Poisson's ratio of 0.5. Mu is 0.5. Okay, sir. Is in the plane stress condition. Plane stress condition means biaxial loading. Sigma x and sigma y will be acting. The displacement field in the plate is given by u is equals to cx square y and v is equal to 0. The displacement field means the change in coordinate u and v is following these relations. Okay, sir. Then story is written. The displacement x and y along x and y respectively are in meters. The stress in the x direction sigma xx is 40 xy. The value of sigma xx is given to you as 40 xy Newton per meter square. Okay, sir. And the shear stress tau xy is alpha x square. The value of shear stress tau xy is alpha x square. And this is also given to you in Newton per meter square. Now what they are saying, the shear stress, okay, then you need to find out the value of this alpha. You need to find out the value of this alpha. Now sir, how to calculate? For calculating this alpha, I have only one relation, that tau xy is equal to g into phi xy. Do I know the value of g? Yes sir, I know the value of g because I know the value of E and mu. So first calculate the value of g. So I will write down E is equals to 2g into 1 plus mu. So E is given to you as 1 is equals to 2G into 1 plus 0.5. So the value of the value of G will be how much? This will be 1.5, this will be 3. So G will be 1 by 3. So the value of G we calculated as 1 by 3, right? And this will be in Newton per meter square. Okay, sir. Then, sir, do I know the value of phi xy? Yes, sir, I very well know the value of phi xy because I know the value of U and V. So I will write down phi xy is equals to phi xy is equal to del U upon del Y plus del V upon del X plus del V upon del X. Please substitute the values. So you have del upon del Y of Cx square Y plus del V upon del X of plus del by del X of 0. Okay. So this term will be 0. This term will be how much? This term will be Cx square. So the value of phi xy will be Cx square. Now, sir, again one problem came here. I don't know the value of C. If somehow I can determine the value of C, I can determine the value of alpha by substituting tau xy is equals to G into phi xy. Now, for giving you this value of C, you have one more relation, that is sigma xx. What is sigma xx? What is sigma xx? Just 1 minute. What is this sigma xx? How we can calculate the value of the sigma xx? So for sigma xx, I know one relation, that for biaxial loading, sigma xx is equal to E upon 1 minus mu square epsilon x plus mu times of epsilon y. Sir, do I know the value of epsilon x and epsilon y? Yes. Epsilon x is equals to del U upon del x. So this is equal to del by del x of Cx square y. Cx square y. So this is equal to 2Cxy. So del U upon del x, which is epsilon x, is equals to 2Cxy. Sir, what is the value of epsilon y? Epsilon y is equal to del V upon del y. Now, sir, V is equals to 0. So del V by del y is also equal to 0. Substitute here. So sigma xx is given to you as 40xy. Sigma xx is given to you as 40xy. E is equal to 1 and mu is 0.5. So I will write down 1 minus 0.5 square. This is equal to 2Cxy plus 0. Get me the value of C from here. So you can see this xy and this xy will going to cancel out. Then you have 1 upon 1 minus 0.25. So this will be 0.75. So 0.75 into 40. So 0.75 into 40 divided by 2 will be the value of C. Please tell me this value of C. Please tell me this value of C. What will be the value of C here? So this will be how much? This will be 3 by 4, 4, 4, 10, 30 by 2 will be 15. So the value of C is coming out as 15. Please check this. Is the value of C coming out to be 15? The value of C is 15. Just quickly tell me the answer for this. The value of C is 15. Yeah, the value of C is 15. Now, sir, I know the value of phi xy, which is Cx square. So I will write down 15 into x square. And I will confidently use this relation that tau xy is equal to G into phi xy. So tau xy is nothing but alpha x square. This is alpha x square. G is equals to 1 by 3 and phi xy is equals to Cx square, and C is nothing but 15x square, right? So from here, x square and x square will cancel out and the value of alpha will come out as 5. The direct answer for this is 5. So this is how you need to deal with this complicated question. You can see everything is used here, everything. Whatever we have written in this slide, everything is used in the previous question. Chalo, moving ahead with this, try this question. So now this is a question from arrangement of the prismatic bars, right? So prismatic bars can be either connected in series or they can be connected in parallel. So this is one arrangement given to you. The question says that the bar having a cross-sectional area of 700 mm square is subjected to axial loads at the position indicated. The value of stress in the segment QR is. So you need to simply find out the value of stress. Now sir, for calculating the value of stress, you should know the value of load. And for knowing the value of load, you should draw the free body diagram. So first, let me consider this and draw the free body diagram for all the segments. So this is the body. This is the body which is subjected to different loads like this. So you have this times 63, this is 35. This is 63, this is 35. This is 63 kilonewton, this is 35 kilonewton. And then you have, this is 49 and this is 21. This is 49 and this is 21. 49 kilonewton and this is 21 kilonewton. Usually whenever these type of question comes in the examination, student face a lot of difficulty to analyze this. Thank you so much Richa for motivating. So whenever you have these type of question coming in the examination, student face a lot of challenges ki sir how to deal with this question. My answer is start from one end and take one block at a time. That's it. Set the equilibrium for one block at a time and keep on moving from one end. Sir, from which end? Any end of your choice. But for me, I have made my certain thumb rules. Every time I see this type of question, I start from the left end. And I start moving from the left end towards the right end, one block at a time, and I'll consider the equilibrium, right? So let me just name this. So this is PQRS. So this is P, Q, R, and S. So quickly draw the free body diagram. First consider this block PQ, and when I am starting from the left, I will only look on this face. If I am starting from the left, I will be only looking on this face. So this is 63 kilonewton. Now in order to keep this PQ in equilibrium, equal and opposite load should act on this side. So equal and opposite 63 kilonewton I will apply blindly without even thinking. Without even thinking, I will apply equal and opposite 63 kilonewton load to make it stable. Now sir, who will going to apply this? This load is applied by portion QR on portion PQ. Now in order to keep this interface in equilibrium, same equal and opposite 63 kilonewton load will be applied by portion PQ over member portion QR. So let me draw the next thing. This is portion QR. So over portion QR, equal and opposite 63 should act like this. This is in reaction to this 63 kilonewton load. Now you have 35 kilonewton acting on this left interface. So I will apply this 35. Now sir, what is the net load acting over this interface? So 63 is acting outwards, 35 is acting inwards. So net load will be 63 minus 35. What is 63 minus 35? What is 63 minus 35? What is 63 minus 35? Please tell me, what is 63 minus 35? What is 63 minus 35? Quickly tell me the answer. So 45, 55, 55, 28. 63 minus 35 will be 28. Please tell me quickly. 63 minus 35 will be 28 or what? What is 63 minus 35? Please tell me the answer. What is 63 minus 35? 28. Very good. So you have net 28 kilonewton load acting on this interface, and that too in the outward, this side. So equal and opposite 28 should act like this. Without even thinking, I am applying this. Equal and opposite 28 should act over here. Who will apply this 28? This portion RS will apply this 28 kilonewton load on this portion QR to keep it in static equilibrium. Very good, Hemant. Very good. Very good. Very good, beta. Very good, Kirti. Now this, in order to keep this interface in equilibrium, equal and opposite 28 should act over this portion RS. Equal and opposite 28 should act over the portion RS. Equal and opposite 28 kilonewton should act over portion RS. So 28 is acting like this. Now external load of 45 is acting inwards. External load of 49 kilonewton load is acting inwards. What is the net load acting over this interface now? So 28 outside, 49 inwards. So net will be inwards and the value will be 49 minus 28. And what will be this value? This value will be 21. Sir, without calculating how you have written, because beta this side 21 is acting inwards, and if 21 will not act on this left side, then how this will be in equilibrium? So this is the free body diagram of all the elements, where this element PQ is subjected to an axial load of 63. This element QR is subjected to an axial load of 28, whereas this element RS is subjected to a compressive load of 21 kilonewton. Now what they are asking? They are asking you to find out the value of stress in the segment QR. Arey bhai, this segment QR. Cross-sectional area 700 mm already given to you. So what is stress on the segment QR? Stress on the segment QR is equal to the load of segment QR divided by the cross-sectional area of segment QR. Divided by the cross-sectional area of segment QR. Calculate this. Stress on segment QR is equal to, what is load on segment QR? So load is, net load on this segment QR is 28 kilonewton. So 28 into 10 raised to power 3 divided by 700 mm square. So this will be in Newton per mm square. Please calculate this and tell me the answer. So this is 1 times, this is 4 times. So 1000 by 4. Sorry, 1000 by, this is 100 and this is 4. So 4000 by 100. So 40 megapascal, yeah. So sigma QR is equal to 40 megapascal. This will be my final answer. So whenever you have this type of question, draw the free body correctly and free body diagram will eventually land into a very good solution for you. So all these are your free body diagrams, FBDs. Chalo, moving ahead with this, please try this next question. This is a question in which the bars are connected in parallel. Please try this. Try this. Please try this question. Very good, Saundarya. Very good, Harshita, very good. Harshita, you are telling me 0.04 in megapascal. The previous answer is 40 megapascal. Try this question. The question says that a rigid bar is suspended by 3 rods made of the same material. So if rods are made of the same material, their Young's modulus will be same, their Poisson's ratio will be same. The area and length of the central rod are 3A and L. So this central rod has a length of L and area as 3A. While that of the other 2 rods, area is 2A and the length is 2L. So for these other 2 rods, area is 2A and length is 2L respectively. If a downward force of 50 kilonewton is applied to the rigid bar, the forces in the central and each of the outer bars will be. Practical application based question. You might see a swing in which when you sit, the platform moves down by the same amount. The platform which was horizontal initially, even after deformation, it is horizontal. A very good question. Check this out. This is the platform and this platform is connected by 3 rods. 3 bars like this. This is 1 rod, outer rod, this is central rod and this is again an outer rod. You just tell me कि if you are applying a load of 50 kilonewton over this bar, what will happen to the assembly? If you will going to apply a 50 kilonewton load over this bar, what will happen to the assembly? The simple answer is कि sir, this platform which is horizontal initially On the application of 50 kilonewton load, it will move downward and it will stay horizontal. Okay, sir, this is the final picture. So when you draw the final picture, it will look like this. This is the final picture of the platform. From this final picture of the platform, what you are observing, observation is very important. If you are very keen in observing the diagrams and the performance of the diagrams, eventually you will land in the solutions very quickly. You just check how my mind is functioning right now. The platform which is horizontal initially, after application of load, it will deform by a certain amount, but it will be again horizontal. So what is my observation here? My observation here is very simple, that this outer bar is undergoing a deformation of delta. This outer bar is undergoing a deformation of delta, and so as the inner bar. This inner bar or this middle bar is also undergoing a deformation of delta, and this bar is also undergoing a deformation of delta. Means all the bars are undergoing common deformations. All the bars are undergoing common deformations. So first of all, the length of this bar is L, area is 3A, length of this bar is 2L, area is 2A, and the length of this bar is also 2A, area is 2A, and the length is 2L. So what is the first equation that I can frame? The first equation is deformation in the outer bar is equal to deformation in the inner bar. Deformation in the outer bar, delta outer, is equal to delta inner. Delta outer is equal to delta inner. If the force developed in the outer bar, if the force in the outer bar causing this deformation is P outer, and the force in the inner bar causing this deformation is P inner. So what I can write here? So here also the force developed is P outer. So from the equilibrium, I can write down P naught plus Pi plus P naught is equals to 50 kilonewton. So first thing is P naught plus Pi plus P naught is equal to 50 kilonewton. So the value of 2 P naught plus Pi is equal to 50. That is the first thing that I got. Okay, sir. That is the first thing I got here, that 2 P naught plus Pi is equal to 50. Okay, now coming back to this deformations. Coming back to these deformations. Sir, how to write down deformation of any bar if it is subjected to axial load? So if a bar is subjected to axial load, deformation of that bar, delta is equals to PL upon AE. Delta of any bar which is subjected to axial deformation is PL upon AE. Now sir, for this outer bar, what is the load? Load is P naught. So I will write down P naught. What is length? Length is 2L. What is A? A is 2A. And Young's modulus is E. For inner bar, load is Pi. What is length? L. What is cross-sectional area? 3A. And what is Young's modulus? E. Why these E's are same? Because both these bars are made up of same material. So this E and E will cancel out. This A and A will cancel out. L and L will cancel out. And this 2 and 2 will also cancel out. So what do you have? So you have P naught is equal to Pi by 3. So you have one more relation between P naught and Pi. You have two equations, two unknowns. Kindly solve and get me the answer. What is required here? They are asking you the forces in the central and each of the outer bars. Means you need to find out all the forces. You can substitute here. You can substitute the value of P naught as Pi by 3. So I will write down P naught is equals to Pi by 3 in this equation. So I will have 2 Pi by 3 plus Pi is equal to 50. So this will be equal to 3. 5 Pi is equals to 150. 5 Pi is equal to 150. So what is the value of Pi? Pi will be equal to 30 kilonewton. Means force in the inner middle bar is 30 kilonewton. So if force in the inner middle bar is 30, P naught will be 30 by 3. So that is equals to 10 kilonewton. Are you getting the same answer? Very good, Saundarya. Very good. Fantastic answer. Loving it. So Pi is equals to 30 kilonewton and P naught is equal to 10 kilonewton. This is the answer. And this is the case of bars connected in parallel. So whenever the bars are connected in parallel, first thing is the sum of forces in the bars will be equal to the total external load. Sum of forces in the bars will be equal to the total external load. The second is the deformations in all the bars will be same which are connected in parallel. Okay, sir. Let's move ahead with this. Try this question. So this is a question from the tapered bar. Please try this. It's a 2017 question, a fantastic one. Please try this. Please try this question. Go for it, go for it. Go for it. So a tapered circular bar. Okay, just giving you the standard result. For example, if there is a tapered bar like this. Tapered bar means diameter is changing over the length. Here the diameter is D1 and here the diameter is D2. The length of the bar is L and this bar is subjected to an axial load of P. If this bar is subjected to an axial load of P, then the total deformation of the bar delta is equals to 4PL upon pi E D1 D2. 4PL upon pi E D1 D2. For example, if you have a tapered bar like this, if you have a triangular trapezoidal tapered bar like this of constant width, if you have a tapered bar like this of constant thickness, sorry, not width, constant thickness T. If you have a trapezoidal tapered bar like this, width here is B1 and width here is B2. The thickness of this bar is T. The thickness of this bar is T. And the length of this bar is L. If it is subjected to an axial load of P, the total deformation of the bar delta is equals to PL upon TE, natural log of B2 by B1 divided by B2 minus B1. Natural log of B2 by B1 upon B2 minus B1. Please have this. Now try the previous question that we have. This is the deformation of the tapered bar, which is having uniform thickness, and this is the tapered bar, circular tapered bar, where the diameter is changing from D1 to D2. Now try this so-called difficult question. So-called, I am saying so-called. For my student, it is one of the easiest question to do. Please try this. An arrangement is shown to you, right? You have a tapered bar connected here and you have a prismatic bar which is present here. And a total load of 30 pi kilonewton is acting here. And what they are asking what is the total deformation of the assembly? Arey bhai, the total deformation of the assembly is simply the sum of deformation of this tapered bar and the deformation of this circular bar. It is very simple. Chalo, check this out. Both the bars will be subjected to a same load of 30 pi kilonewton. Let's see this. So this is your tapered circular bar. And then you have a cylindrical bar at the bottom. Like this. And you have a 30 pi kilonewton load acting like this. and it is connected from here, it is fixed from here. Okay. So let me name this. This is A, B and C. Again, if you draw the free body diagram, you will realize that both the members are subjected to only one load, and that is 30 pi kilonewton. If I draw the free body diagram of this portion BC, how it will look like? It will look like this. This is the free body diagram of portion BC. This portion BC is subjected to 30 pi kilonewton load like this. The diameter of this is given to you as 10 mm and the length is 1.5 meter. This length is 1.5 meter and the diameter, this diameter D1 is given to you as 10 mm. So sir, what is the deformation of this bar BC? So deformation of this bar BC delta 1 is equals to PL upon AE. Reason being, it's a prismatic bar, and for prismatic bar deformation delta is equal to PL upon AE. Very good, Saundarya. All of you keep answering this. Harshita ma'am. Delta 1 is equals to PL upon AE. What is the load acting over the bar? Load acting is 30 pi. So this is 30 pi. Now it is in kilonewton. So I will write down 10 raised to power 3. Okay, sir. Then length of the member is 1.5 meter. So I will write this as 1500 mm divided by the value of area. Area is pi by 4 into 10 square. Then you have E. The value of Young's modulus is given to you as how much? The value of Young's modulus is 2 into 10 raised to power 5 megapascal. So this will be 2 into 10 raised to power 5. Please calculate this. I think this will come out as 9 mm or how much? Very good, Avinash, very good. Please tell me this answer first. What is the value of delta 1? Please tell me the value of delta 1. First tell me the value of delta 1, whether it is 9 mm or 5 mm, 6 mm, sorry. Total answer is absolutely correct, 15 mm. But first tell me this delta 1. Please tell me this value. What will be the value of delta 1? Please tell me delta 1. So you calculate this, right? This will be delta 1. Now coming to this tapered bar. So this tapered bar is also subjected to a load of 30 pi kilonewton from the either side. The diameter here D1 is 10 mm and the diameter on the other side D2 is given to you as 20 mm. I think length of this portion is 2 meter. Just check. Length of this portion is 2 meter, yeah. This length of this portion is 2 meter. So delta 2 is equal to 4 PL upon pi E D1 D2. So this is equal to 4 into P. P is 30 pi kilonewton. Please keep a check on the units. So 30 pi into 10 raised to power 3. Length is 2000. Length is 2000 divided by pi E. E is 2 into 10 raised to power 5 megapascal and D1 D2. So 10 into 20. Please tell me this answer. 9 mm. Okay. This delta 1 is 9 mm. Delta 1 is 9 mm. Calculate delta 2. I think this will come out as 6 mm. Calculate this. Delta 2 will be how much? I think this will be 6 mm. So total will be 15 mm. Delta 1 plus delta 2 will be the total deformation of the bar. That will be 15 mm. So total deformation delta is equal to delta 1 plus delta 2. So this is equals to 9 plus 6 mm. So that will be equal to 15 mm. Absolutely correct, Avinash sir. Yeah, so that is 15 mm. Very good, very good, very good, beta, very good. Let's move ahead to the next question. Okay. Try this. The question says that a solid cube of side 1 meter is kept at a room temperature of 32 degrees Celsius. The coefficient of linear thermal expansion of the cube material is 1 into 10 raised power minus 5 per degree Celsius, and the bulk modulus is 200 gigapascal. If the cube is constrained all around and heated uniformly to 42 degrees Celsius, initially it is at 32 degrees Celsius and it is heated to 42 degrees Celsius, then the magnitude of volumetric mean stress in megapascal induced due to heating is. Those students who have confusion in thermal stresses, for them my simple advice is, just observe my drawings, okay? Only observe my drawings and you will understand everything about thermal stresses. For example, this is a bar which is kept on a horizontal frictionless surface. What it is? It is a bar which is kept on a horizontal frictionless surface. If I increase the temperature of the bar, what will happen? If I increase the temperature of the bar, this bar will undergo free expansion. There will be no stresses induced in the bar. This bar will undergo free expansion because this bar is not restrained from any direction. If you decrease the temperature, this bar will undergo free contraction because nobody is stopping the bar to contract itself when the temperature is reduced. So this is the beauty of thermal stresses. Thermal stresses will only be induced if you restrict the bar from free expansion or free contraction. If the material is allowed to expand freely, then there will be no thermal stresses. But if the material is restrained along any one particular direction or along any direction, like 2-3 directions, then thermal stresses will be induced in the bar. Now I am telling you one very important thing. Thermal stress is the property of the material. And we are talking about isotropic materials. So if we are restraining the bar in 3 directions, first thing is, in all the 3 directions, thermal stresses will be induced with the change in temperature. In this question, what they are saying is, you have a metal cube like this. You have a metal cube like this. This is the metal cube, right? This metal cube is restrained along all the directions. This metal cube is restrained along all the directions. Along all the directions, this metal cube is restrained. This metal cube is restrained along all the directions, X, Y, Z, all the direction, right? Now, if you increase the temperature of this metal from 32 degrees Celsius, to 42 degrees Celsius, so the delta T is 10 degrees Celsius. What will happen in this 10 degrees Celsius? Due to increase in temperature, the body is trying to expand itself. But the supports or the restraints in all the 3 directions is not allowing the body to undergo free expansion. Due to which in all the 3 directions, there will be the development of thermal stresses. There will be the development of thermal stresses along X direction, like this. There will be compressive thermal stresses. Why compressive, sir? Because with increase in temperature, the body is trying to expand, but the support is trying to compress the body, is not allowing the free expansion. That is why compressive thermal stresses are developed along X direction. Similarly, compressive thermal stresses are induced along Y direction. Compressive thermal stresses are induced along Y direction. And similarly, compressive thermal stresses like this, compressive thermal stresses are induced along Z direction. I said, all these thermal stresses induced are the property of the material. Means sigma x is equal to sigma y is equal to sigma z. All these thermal stresses are the property of the material. Just for writing the equation, I write it like sigma x, sigma y and sigma z, so that while writing the equation, I don't get confused at any point. Check this out. How to write the equation? How to write the equation of thermal stress? the equation of thermal stress, you can take any direction, right? So if you observe the x direction, what is a net deformation along x direction? So delta net along x is equal to 0. For writing delta net along x, first I will write down the free expansion along x direction due to increase in temperature. So delta net along x is equal to free expansion along x minus effect of sigma x, You can see this. With increase in temperature, the body is trying to expand, that is free expansion. Then sigma x is trying to compress the body. The Poisson's effect of sigma y is increasing the length of the member. This is compressive, so Poisson's effect will increase the length. Similarly, the Poisson's effect of sigma z will also increase the length along x direction. So plus effect of Poisson's effect of sigma y and sigma z, and this should be equal to 0. Now check this out. What is free expansion? Free expansion is L alpha delta t. Effect of sigma x is minus sigma by E into L. I know that, right? This I have written just to write the equation properly. But at the core of my heart, I know that sigma x is equals to sigma y is equals to sigma z is equals to sigma, and this sigma is nothing but the mean volumetric stress. This is mean volumetric stress. What they are asking. Mean volumetric stress. So this is effect of sigma x. Now effect of sigma y will be plus mu times of sigma by E into L, plus effect of sigma z plus mu times of sigma z by E into L. Please calculate this. You can take out L common. So L is common. You are left with alpha delta t minus sigma by E into 1, this will be 1 minus 2 mu. This is equal to 0. So from here, what is the value of sigma? Sigma is equals to E alpha delta t upon 1 minus 2 mu. Now sir, they have given you the value of alpha, they have given you the value of delta t, but they don't give you the value of E and mu. Instead of E and mu, they have given you the value of bulk modulus. See what we have read like 1.5 hours back, it is again coming back into use. So they don't give you the value of E, they don't give you the value of mu, but they have given you the value of K. Why? Because E is equals to 3K into 1 minus 2 mu. So E upon 1 minus 2 mu can be written as 3K. So instead of E upon 1 minus 2 mu, you have to substitute 3K. So sigma is equals to 3K into alpha into delta t. 3K into alpha into delta t. Substitute the value, get me the answer. So sigma is equals to 3K alpha into delta t. So you have alpha 1 into 10 raised to power minus 5 per degree Celsius, and K is 200 gigapascal. So this is equal to 200 gigapascal. So 200 into 10 raised to power 3 megapascal. Alpha is 10 raised to power minus 5 and delta t is 10. Please calculate this and tell me the answer. So this will be, I think, 10 raised to power 5. So I think this will be 20 megapascal sigma. Please tell me this will be 20 megapascal. Please tell me the answer. Is it 20 megapascal? Is it 20 megapascal? Just confirm. Kindly confirm this. Please tell me the answer. 20. Yeah, right. Okay. Let's move ahead with this next question. Please try this. A fantastic question asked for mechanical engineering. The question says that a circular metallic rod of length 250 mm. The length of this rod is 250 mm. It's a circular metallic rod. Placed between two rigid immovable walls as shown in the figure, the rod is in perfect contact with the wall on the left side and there is a gap of 0.2 mm between the rod and the wall on the right side. They could have directly given you the figure instead of writing this whole story. Okay. If the temperature of the rod increases by 200 degrees Celsius, the temperature of this rod will increase by 200 degrees Celsius. Okay. The axial stress developed in the rod is, first thing is, when the axial stress will not develop in the rod. What is the condition that axial stress will not develop in the rod? The condition is very simple. If the free expansion of this rod is less than 0.2 mm, then there will be no stresses developed in the bar. But if the free expansion of this rod is more than 0.2 mm, then only axial thermal stresses will be developed, and that too only along x direction. Okay, check this out. So first calculate the free expansion. So free expansion of the rod is L alpha delta T. What is the length of the bar? Length of the bar is 250 mm. Alpha is how much? Alpha is, they have given you as 10 raised to power minus 5. And delta T is how much? Delta T is 200 degrees Celsius. Please calculate this. This will come out in mm because length you have substituted in mm. Please get me the answer for this free expansion. Please calculate this free expansion and tell me the answer in mm. Quickly, we have to start with shear force and bending moment diagram after this. Go for it. Please tell me the value of this. So this will be how much? 3 zeros, 50, 4 zeros. So this will be 3. So 25 into 250 into 3 zeros into 10 raised to power minus 5. So this will be 0.5. You can see this. The free expansion of the bar is 0.5 mm. The free expansion of the bar is more than this gap. Hence, thermal stresses will be induced in the bar. Very good, Harshita. Very good. It is 0.5 mm. Since this is more than 0.2 mm, therefore, thermal stresses will be induced in the bar. Now check this picture. This is the final picture of the bar. This is the final picture of the bar. When it has expanded completely, okay, this was the initial picture of the bar. This was the initial picture of the bar. This is the initial picture of the bar, and finally the bar expanded by 0.2 mm. So what is delta net of the bar? So I will write down delta net of the bar is 0.2 mm. What is delta net of the bar? Now you can see this. This bar will be experiencing axial thermal stresses like this when it will expand by 0.2 mm and it starts in its want to expand more. So till 0.2 mm there will be no thermal stresses, but the moment it wants to expand more than 0.2 mm, then thermal stresses sigma will be induced in the bar, right? So delta net for this bar is equal to free expansion of the bar minus effect of sigma. Minus effect of sigma is equal to 0.2 mm. What is free expansion of the bar? Free expansion of the bar is length of the bar alpha into delta T minus effect of sigma, which is sigma upon E into L. This is equal to 0.2. Substitute all the values. So length of the bar is free expansion you have already calculated 0.5. Then this will be minus sigma by E into L is equal to 0.2. Calculate this value. So sigma by E into L, L is 250, is equal to 0.5 minus 0.2. So this is equal to, sigma is equals to 0.3 into E. Now what is the value of Young's modulus? The value of Young's modulus is 200 gigapascal. So this is 200 into 10 raised to power 3 megapascal divided by length of the bar, which is 250 mm. Please tell me this answer. Please tell me the value of sigma, stress induced in the bar. So 0.3 into 200 into 10 raised to power 3 upon 250. Please tell me the answer for this. What is the value of sigma here? That is the amount of thermal stress that will be induced in the bar. Please calculate this. So 0.3 into 200 by 250 into 10 raised to power 3. Please calculate this. Do it. We have to start with shear force and bending moment diagram. Harshita, Saundarya, Vinash, please sir, answer me quickly. Kirti, please answer me quickly. It is 240 megapascal, okay. All of you just confirm this. This is 240 megapascal. megapascal, very good. So this answer is 240 megapascal of the stress. This is the thermal stress induced in the bar. And how we have calculated? By writing this compatibility equation. Okay, let's move ahead with the next thing. My dear students, again I would just like to remind you, you see, when you practice question, although almost like whatever concepts you have read starts coming to your mind, and that is why tests are very important. So if you are an enrolled student, this is my personal advice, start giving you the test series. And if you are non-enrolled student, again, I am giving an announcement. We are offering you the test series plus course at a discounted price of 20%, where we are providing with the test series along with the gate question bank of maths aptitude and technical subject. Now, first of all, let's see this question. This is a question in which you need to find out the support reaction at the roller support at A. Over the years, I have seen that whenever this term support reaction comes, students start doing so many things. Like they will start writing whatever they know. Arey my dear, you have to first understand why the support reactions are coming. What is the role of the support reactions? For example, if this is my body and if this body is not supported, okay, on the application of load, this body will start undergoing rigid body translation. This type of translation you study in engineering mechanics. But in strength of material, there will be a support to hold this structure into its initial position. Means the body, whatever we analyze, is under the state of rest. It will not be moving. Now, for example, if I have hold this body from this point and I apply any axial load, will this body will going to move? No. Reason, there is one horizontal reaction acting like this, which is holding back this body into its initial position. Similarly, if I apply any vertical load over the body, again the body will not undergo any vertical displacement. Reason is, there is a vertical support reaction here. So how to calculate the support reaction? By applying the equations of static equilibrium. Now this name sounds like, my God, what is the equation of static equilibrium? Static means at rest. So whatever equations you write considering body at rest is the equation of static equilibrium. From where we derive this equation? Check this out. What is Newton's second law? Newton's second law is F net. Newton's second law is F net is equals to m into a. Right? If acceleration is 0, what is the net force? Net force will be also equal to 0. F net will be equal to 0. if I am saying the body is at rest, means the body is not moving in the horizontal direction. The horizontal acceleration of the body is 0. And if horizontal acceleration of the body is 0, means F net in the horizontal direction is 0. And the manner in which we write F net is nothing but the summation of horizontal forces equal to 0. This is nothing but net force acting in the horizontal direction. The second equilibrium equation is net vertical force is equal to 0. Means if the body is at rest, means there is no acceleration in the vertical direction. And if there is no acceleration in the vertical direction, then the net force acting in the vertical direction has to be 0. Third condition, if the body is at rest, means the body is not rotating about any point. And if the body is not rotating about any point, means the net moment acting over the body is equal to 0. Now this net moment can be written about any point. So I will write down summation of moment about any point on the structure. Summation of moment about any point on the structure is equal to 0. And these three are called as equations of static equilibrium. Equations of static equilibrium. Equations of static equilibrium. These are called as equations of static equilibrium. Only these equations of static equilibrium are used to find out the support reaction. These are used to calculate support reaction, nothing else, nothing else. Only these equations of static equilibrium are used to find out the support reaction, nothing else. See this question. The question is saying that you have a beam A, B, C, and you have 2-point load, one acting here, another point load acting here. This length is L by 2, this length is also L by 2, this length is also L by 2. What they are asking is, they are asking to find out the reaction at the roller end A. So this is your roller support A. You need to find out the support reaction at A. How we can calculate this support reaction? Anyone? How we can find out the value of this support reaction? I will write down this as HA. How can I find out the value of this support reaction? You can see this C is a hinge support. So you have VC acting vertically upwards and you have HC acting like this. How can I find out the value of this HA? Anyone? Can anybody tell me how can I find out the value of this support reaction HA? Anyone? You have three equations of static equilibrium to be used. Where? Option D, HA is equal to 0. Okay. But Avinash sir, how to calculate this HA? How you have calculated? How you came to this conclusion that HA is 0? How do you came to this conclusion that HA is 0? What you need to do is, you see this point C, right? If you stand at this point C and you write down summation of moment about this point C, then moment due to HC and VC will become 0, because line of action of HC and VC is passing through point C. So I will write down summation of moment about C equal to 0. Okay. Now for writing the moment, I will start from the left side. So first, HA into L will give you the clockwise moment about C. So I will write down HA into L, giving the clockwise moment. Then you have the anti-clockwise moment due to this load P. Value will be P into L by 2 and it is anti-clockwise. So I will write down minus P into L by 2. Minus P into L by 2. Total moment about A is 0. Beta, if you write down total moment about A 0, then the moment due to HA will be 0. There will be no moment due to HA. And HA will not come into play. HA will come into play if you write down moment about C equal to 0. Okay. So we were writing summation of moment about C equal to 0. So we have written moment due to HA. Then we have written moment due to this external load P. Now coming to this moment due to external load this P. This will give you the clockwise moment, value will be P into L by 2. So plus P into L by 2. this should be equal to 0. Now this P into L by 2 and P into L by 2 will cancel out, and the value of HA from here will come out as 0. The value of HA from here will come out as 0. So whenever you have the equations of static, whenever you have to calculate the support reaction, you will calculate it using equations of static equilibrium. Chalo. One of the favorite variety of question in mechanical and civil, asked for 100 of times. 100 means many times, not literally 100 of times. Many times they have asked this question. This question says that the magnitude of reaction force at joint C, this is your roller support, they are asking you how much is the support reaction that will develop here. And for this beam, an internal hinge is present at B. Now honestly tell me, first of all, how many of you have confusion in dealing with the internal hinge? How many of you still feel that, ki sir, whenever internal hinge is present, I'm not sure how to analyze it? Just comment quickly. And how many of you are comfortable? Those people also comment quickly. How many of you are not comfortable and comfortable with internal hinge? Just comment quickly. Because this is one of the most favorite variety of question they frame every year. In every alternate 2-3 years, I've seen a lot of questions, especially for mechanical engineering students. God knows why they love this propped cantilever beam so much with an internal hinge. Just quickly comment, how many of you are comfortable with the internal hinge and how many of you are not comfortable with the internal hinge? As you people are the students and I am here to teach you, that is why I want an honest answer. Chalo, please quickly tell me. I'm waiting for your answers. Quickly tell me. Still waiting for your answers. How many of you are comfortable with internal hinge and how many of you are not comfortable with internal hinge? How to deal with that? Not comfortable. That is a great answer. That kind of answer I love. When the student wants to learn something, right? I'm literally enjoying teaching those students who are literally honest. Even if you are this much not comfortable with the internal hinge, kindly comment. And if you are comfortable, especially our classroom students, if you are comfortable, then also you should comment ki sir, I am so much comfortable in dealing with internal hinges. Whenever the internal hinges are present, I am comfortable. Avinash has given me the answer. Very good, my dear. Very good. Fantastic answer. Now, first of all, whenever internal hinge is present, how do we analyze this? I will not go into the complete discussion. I will give you one briefing. Okay. For example, this is my beam. This is my beam. This beam can be subjected to any load. This is my beam and this beam can be subjected to any load, right? And there is one internal hinge present here. There is one internal hinge. Say this point is say this point is A, this point is B, and this point is C. Okay. I tell you one very interesting thing. If you write down the equation of static equilibrium, what does equation of static equilibrium says? Equation of static equilibrium says that summation of moment about B equal to 0. When you write this, you have to stand at B and you have to write down moment due to all the loads that are acting over this beam AC. So in this, moments due to all the loads, moments due to all the loads, acting over AC. Moments due to all the loads acting over AC about B you have to write. About B you have to write, and this you can write even when there is no internal hinge. But if internal hinge is present, then what is the new thing that you get? Internal hinge basically tells you that there will be no moment transfer from portion AB to portion BC. There will be no moment transfer from portion AB to portion BC. Whenever internal hinge is present, we get one added advantage. And what is that advantage? That advantage is this equation. Summation of moment about B on portion BA equal to 0. Means this we can only write when we have an internal hinge. So what we need to do is we need to stand at this internal hinge and we have to only observe this portion AB. And you have to only write summation of moment on this portion AB equal to 0. The another advantage that we get by the presence of internal hinge is summation of moment about B on portion BC equal to 0. Means whenever internal hinge is present, now it is my choice. Either I can write down summation of moment about this internal hinge over the entire length of the beam equal to 0, or I can stand over this internal hinge and I can write down summation of moment only on the left of hinge equal to 0, or I can write down summation of moment about this hinge on the right of hinge equal to 0. Three equations I can develop using the internal hinge. When you are writing MBA equal to 0, summation of moment about B on portion BA equal to 0, you have to stand at B and you have to only observe this portion till the end of the beam. Okay. When you are writing this summation of moment on portion BC equal to 0, means you have to stand at B and you only have to observe the right side of this portion. Right. Chalo, let's see this question. So you have a cantilever, propped cantilever beam like this. This is your roller support here. And there is one internal hinge present here. So this is a 50 kilonewton load acting at 3 meter distance. This is the 50 kilonewton load acting at 3 meter distance. Those who have calculated this support reaction, get me the other values of support reactions. And you have a UDL of 10 kilonewton per meter acting on this side. So this is a 10 kilonewton per meter acting on this side. I want all the support reactions, okay? Question is only asking you to calculate support reaction at C, but I want all the support reactions. So this is 3 meters, this is 3 meters, and this is 4 meters. This is point A, this is B, and this point is C. This is the vertical reaction VC, okay. Here you have one vertical reaction VA, one horizontal reaction HA, and one moment reaction like this MA. So I have just assumed the direction of these support reactions which are present here. Now due to this internal hinge, what is the added advantage? The advantage is I can stand at this point B and I can only consider the right of this portion B, and I can write down summation of moment about B on portion BA equal to 0. So first you will have a clockwise moment due to this UDL. Value of this moment will be 10 into 4 is the total load. So 10 into 4 is the total load multiplied by the distance between CG of this UDL and this point B, which is 2 meter. So into 2, that is your lever arm. Now this VC will going to give you the anti-clockwise moment about B. Value will be minus VC into 4. So the value of VC will come out as 20 kilonewton. Avinash sir, Harshita ma'am, all of you have answered it correctly. Very good, Ashok, very good. All of you have answered this correctly. Kirti ma'am, are you comfortable now? Kirti, Ilangana ma'am, you are comfortable now with this internal hinge? Ilangana KS. We have a student called Kirti KS. So I thought Are you comfortable now with this? Okay. Now you need to find out the other support reaction. So first thing is, what you need to do is, yes sir, okay. Now what you need to do is, you need to write down summation of horizontal forces equal to 0. So that will going to give you the value of HA. So I will write down summation of horizontal forces equal to 0. How many horizontal forces are present? Only HA is present. So I will write down HA is equal to 0. So horizontal reaction HA is equal to 0. Okay, sir. Now next, for calculating VA, write down summation of vertical forces equal to 0. So summation of vertical forces equal to 0. So you have VA acting upwards, VC acting upwards, and these two loads acting downwards. So I will write down plus VA plus VC minus 50 and minus this total load due to UDL. Minus 50 minus 10 into 4 is the total load due to UDL. Substitute the value of VC and get me the value of VA. What will be the value of VA? So this will be 50 plus 40 minus 20. Please get me the value of VA. Please tell me the value of VA from here. So 50 plus 40, 90, 90 minus 20 will be 70. So VA is equals to 70. So VA is equal to 70 kilonewton. Now sir, how to calculate this moment reaction MA? Arey sir, very simple. You can use any equation. So many are there. Very good Harshita, very good Elangna. There are so many equations I can use, right? For calculating this MA, what all equations I can use? I will tell you. First, I will write down summation of moment about A equal to 0. One equation. Another equation is summation of moment about B on portion BA equal to 0. This can be used. Or summation of moment about B equal to 0. Or I can write down summation of moment about C equal to 0. You can use any equation. My dear, when you are comfortable with these equilibrium equation, you will get a next level confidence. Especially in strength of material, because in almost every chapter of strength of material, if you leave bending and shear stresses and thin pressure vessels and columns analogy, you need to calculate support reactions. You require support reactions. And if you also leave principal stresses and strain for deflection, drawing shear force and bending moment diagram, you require these support reactions. So you can use any of this equation to calculate the value of MA. You tell me 1, 2, 3, 4, which equation I should write? You only tell me 1, 2, 3, 4, which equation I should write? Which you feel is the hardest equation to write, you tell me. I will write that. I think Avinash sir will answer, sir, every equation that is written is easy for me. You just tell me which equation I should write in which you are not comfortable. You tell me that and I'll write that equation. I'll write that equation for you, tell me. Which equation I should use to find out the value of MA, and you tell me the hardest one in which you will be having a lot of confusion to write. Please tell me. Which equation? Second equation. Yeah, very good answer. Second, MBA. So you need to stand at this point B and you have to only observe this side, left side of the beam. So when you write down summation of moment about B on portion BA equal to 0, First thing you will observe is you will have this anti-clockwise moment MA. So I will write down minus MA. First thing is this anti-clockwise moment MA. So I will write down minus MA. The line of action of HA is passing through point B. So there will be no moment due to HA, right? Then you have VA giving the clockwise moment about point B. Value will be VA into 6. So I will write down plus VA into 6. Then you have this 50 kilonewton load giving the anti-clockwise moment about point B. So value will be minus 50 into 3. Minus 50 into 3. And this is your second equation. This one is your second equation. Substitute the value of V and get me the value of MA. So MA will be equal to VA is 70. So this will be 70 into 6 minus 50 into 3. So 7 6 are 42. 420 minus 150 will be how much? What is 420 minus 150? Please tell me the answer for that. 420 minus 150. That will be your MA. Please calculate this. It is 270. Very good, Saundarya. So MA will be equal to 270. MA will be equal to 270 kilonewton meter. Now, sir, let's move ahead with the next question. Okay. The question says for the overloading beam shown in the figure, the magnitude of the maximum bending moment. But before bending moment, shear force needs to be discussed, right? So first of all, what do we mean by shear force? What is this shear force? What is this shear force? What is this shear force? Right. So in simple words, shear force means the force acting along the surface. That is your shear force. If your force acts along the surface, then it is identified as a shear force. Now see this. Shear force diagram, SFD is the variation of shear force. SFD is the variation of shear force. Is the variation of shear force along the length of the beam. Along the length of the beam. Very important thing. Length of the beam. Usually you people are very much comfortable in drawing the shear force diagram, that I know. But I want to give you one basic. Okay. All the discussions we have already done in the class, but one basic is very important. Shear force at any section is the sum of transverse loads. Transverse means perpendicular to the axis of the beam. Sum of the transverse loads acting either towards left or right of the section. Now, if I draw one beam like this, and this is a beam which is fixed here. This is the beam which is fixed here. Now, if I am applying the transverse load like this is my first transverse load. Please observe this very carefully because I'm in a mood to give you those concepts which you will not find in much clarity anywhere in this world. What I'm saying, anywhere in this world. Anywhere in this world. Please check this out. This is one set of transverse load which is acting in the vertical plane, right? These set of transverse loads will going to give you the shear force in the transverse direction, means vertical direction. These set of transverse loads will going to give you the shear force in the transverse direction like this. These set of transverse loads will going to give you in the transverse direction like this. So if a beam is subjected to vertical loading, that vertical loading can be downwards or upwards, doesn't matter. You will get one shear force diagram corresponding to one set of loading. If you have two sets of loading, means if the load is acting on the vertical plane and simultaneously in the horizontal plane, you will get two shear force diagrams. Because vertical loading will give you shear force like this in the vertical plane. Horizontal loading will going to give you the shear force in this direction, in the horizontal direction. You will get the shear force in the horizontal direction if this beam is loaded horizontally like this. If this beam is loaded horizontally like this, you will get another set of shear force diagram. So vertical loading will give one shear force diagram, horizontal loading will give one shear force diagram. What is the common confusion here? For example, say this is force F1 here, force F2 here, force F3 here, and this is for F4. And if I ask you what is the value of shear force over this section XX? So first you should ask me, sir, should I calculate shear force due to vertical loading or should I calculate shear force due to horizontal loading? Don't add them simultaneously, please. Shear force due to vertical loading will be one shear force and shear force due to horizontal loading will be the other shear force. Okay. Acting over the same cross section, direction of both the shear forces will be different. Shear force due to vertical loading will act in the vertical direction and shear force due to horizontal loading will act in the horizontal direction. Please keep a check on this. So first of all, shear force due to vertical loading is equal to shear force over this section XX due to vertical loading. So on the right of the section, I will take downward load as positive. So I will write this as F1 plus F2. Similarly, shear force due to horizontal loading, right? So only one horizontal load is acting, that is F3. So I will write down shear force due to horizontal loading is F3. So what is the important point here? Write a note and keep this with you. Vertical loading will give one SFD considering only vertical loads, where only vertical loads are considered. And horizontal loading will give another SFD where only horizontal loads are considered. Now sir, what is the point of confusion here? The point of confusion here is both these vertical loads and horizontal loads are transverse loads. So when I say that shear force over any section is sum of the transverse load either on the left or right of the section, by that what I mean is, if you are writing shear force due to vertical loading, you have to only consider vertical loads. If you are writing shear force over a section due to horizontal loading, you have to only consider the horizontal loads. And same goes with the bending moment diagram. If you are drawing bending moment diagram due to vertical loads, that load will cause bending about Z direction. So that is your MZ. So variation of MZ will be one bending moment diagram. If you are drawing bending moment diagram due to horizontal load, that will going to cause bending in the Y direction, right? It will be bending about Y direction. So that is a variation of MY from this to this end. So whenever you have biaxial loading or loading in two different planes, you will get two different shear force diagram and two different bending moment diagrams. Okay, so that is a new thing here that you need to consider. Now, there is a short trick for drawing shear force diagram. What is a short trick? It's a very simple short trick. The short trick says that if you have a point load, and the point load is acting upwards, then you need to move up in the shear force diagram. If point load is acting downwards, so you need to move down in the shear force diagram. This is about shear force diagram I'm talking, okay? Only about shear force diagram. If your point load is acting upwards, you need to move up. If your point load is acting downward, you need to move down. If you have a downward acting UDL like this, whose value is W and the length over which this UDL is acting is L. So first of all, over this length L, in the shear force diagram, you need to move linearly like this. And the slope of this line will be minus W. And this total downward displacement that you need to do will be equal to W into L. So whenever you have a downward acting UDL, you need to move down by the amount of W into L. If you have an upward acting UDL like this, whose intensity is W, length is L, then in the shear force diagram, you need to move up linearly like this, and the slope of this line will be plus W, and this total upward movement will be equal to W into L, which is total load due to this UDL. The next important point is whenever concentrated moment is acting, there will be no change in shear force diagram. And when there is no load acting over a span, then shear force diagram will be constant. These are the short tricks for drawing the shear force diagram, and these short tricks will literally help you in drawing the shear force diagram in no time. Literally no time means, I mean literally no time. So this is the short trick for drawing the shear force diagram. This is the short trick for drawing shear force diagram. One second. Short trick of SFD. Short trick of drawing shear force diagram. Chalo. I will give you one beam. Quickly draw the shear force diagram for this beam. This is the cantilever beam, which is subjected to multiple point loads like this. One point load is acting here, another point load is acting here, then you have another point load acting here. All the distances are 2 meters. This is 40 kilonewton, this is 10 kilonewton, and this is 90 kilonewton. Please draw the shear force diagram for this. You have 2 minutes of time, just go for it. Draw the shear force diagram for this beam. And I'm telling you, the first thing is you need to find out the support reaction, and then you need to draw the shear force diagram. Please do it. Comment the value of support reaction in the comment box. So how to calculate the support reactions here? Very good, Avinash. Very good. Avinash sir is saying, sir, M is equals to 580 kilonewton meter anti-clockwise, F is equals to 120. Okay, very good. Here, for drawing the shear force diagram, I only require the vertical support reaction. Okay, moment reaction will not cause anything. I just require the vertical support reaction here. So first calculate the value of V1. For calculating V1, what I can do is, I can simply write down summation of vertical forces equal to 0. I can simply write down summation of vertical forces equal to 0. So V1 is acting upwards, this 40 is downward, 10 is upward, 90 is downward. So minus 40 plus 10 minus 90 equal to 0. So the value of V1 will be how much? V1 will be equal to, this will be 130, 130 minus 10 will be 120. 120 kilonewton, okay. Check this out. I only require the value of V1 for drawing the shear force diagram for this beam. Check this out. So at this point, you have V1 acting upwards. So I will move up by the amount of V1, that is 120. So I'll move this up by the amount of 120. So I'll move this up by the amount of 120. So this is an upward movement of 120. So the value of shear force here is 120. Now between these 2 points, no load is acting. So shear force diagram will be constant. So between these 2 points, shear force diagram will be constant. Then at this point, you have a downward acting load of 40. So I need to move down by the amount of 40. You have to check this downward movement is 40. So if this downward movement is 40, what will be the value of this ordinate? What will be the value of this ordinate? So 120 minus 40 will be 80. So the value of this ordinate will be 80. This ordinate will be 80. Now again between these 2 points, there is no load acting. So shear force diagram will be constant like this. At this point, you have to move up by the amount of 10. So I need to move up by the amount of 10. So if this upward movement is 10 kilonewton, so what will be the value of this ordinate? So this will be 80 plus 10, that is 90. Again between these 2 points, there is no load acting. So shear force diagram will be constant. And at this point, you have a downward acting load of 90. So I had to move down by the amount of 90. So this downward movement here is 90. Check this out without any calculation. Like only by calculating the support reaction, I have drawn the entire shear force diagram just by using the short tricks. Okay. So this entire shear force diagram will be positive. You have to write down all the ordinates. This will be 90. This will be 120, and this is your shear force diagram for the beam. Okay. Chalo, on the same note, draw the shear force diagram for this beam. Shear force diagram for this beam. This is point A, this is point B, this is C, this is D, and this is E. This is 2 meter, this is 1 meter, 1 meter, and again 2 meter. You need to draw the shear force diagram for this beam. Okay, again use the short trick and draw the shear force diagram. You require only the vertical reaction here. First of all, tell me what will be the value of vertical reaction at A. Tell me the vertical reaction at A. Please do that. first tell me what will be the value of vertical reaction at A. Please do it. Vertical reaction at A. Get me the value of this VA. For cantilever beam, it is very easy to find out vertical reaction. You have to just write down summation of vertical forces equal to 0. Do it, do it. Get me the value of VA. Avinash, very good. Harshita, Avinash, both of them are answering 150. Okay. So let's write down summation of vertical forces equal to 0. So you have upward acting VA. So I will write down plus VA. Then this UDL acting downward. So total load due to UDL will be 80 into 2 meter. So minus 80 into 2. Then this point load is acting downward. Value will be minus 40. And this point load is acting upwards. Value will be plus 50. So VA is equals to. So 180 into 2 will be 160. 160 plus 40 minus 50. So this will be 150. So VA will be equal, VA will be equal to 150. VA will be equal to 150 kilonewton. Use the short trick and draw the shear force diagram. Use the short trick and draw the shear force diagram. This is B. C. D, this is E. Okay. So at this point A, you have VA acting upwards. Very good, Saundarya. 150 is the correct answer. So VA is acting upwards. So you need to move up by the amount of 150. So this is an upward movement of 150. So here the value of shear force is 150. Now between A and B, there is no shear force acting. There is no load acting, sorry. There is no load acting. So the value of shear force will be constant. Okay, sir. Then from B to C, don't move to B to D because there is a point load acting here. Okay, and wherever there is a point load, there will be change in ordinate. So move from B to C. From B to C, UDL is acting and this UDL is acting downwards. The magnitude of the total load due to UDL is 80 into 1. So this is 150. Your UDL is acting downwards like this. So I need to move linearly downward like this. Now what is this downward movement? This downward movement will be 80 into 1. So this downward movement will be 80 into 1, that is 80. So what will be the value of this ordinate? What is 150 minus 80? What is 150 minus 80? Can you tell me? What is 150 minus 80? 150 minus 80 will be 70, I guess. Just check. 150 minus 80 will be 70, yes or no? So this downward movement will be 150 minus 80, that is 70. Let me draw this. So this is 70. So this downward movement is 80. If this downward movement is 80, so this will be 150 minus 80. So this will be 70. Now after this, you have a downward acting point load. So at this point, you need to move down by further 40. So you need to move down by further 40. So when you move down by further 40, this value will be equal to 30. Right? This value will be equal to 30. And then over this portion CD, again you have a UDL of 80 kilonewton per meter acting. So again you need to move down by the amount of 80 into 1. So again you will going to have a downward movement like this, which is 80 into 1. This downward movement here is 80 into 1, that is 80. So what is 30 minus 80? 30 minus 80 is minus 50. So here the value of shear force will be minus 50. Then from D to E, there is no load acting, so shear force diagram will be constant. And at E, you have an upward acting load of 50 kilonewton. So here this will be minus 50. So let me just clean this thing. And this is your shear force diagram of the beam without even a single calculation apart from the support reaction. This is positive here and this is negative here, and this is your shear force diagram SFD. So without even using any calculation, we have drawn the shear force diagram. Okay. Literally speaking, I brought question till shear these bending and shear stresses today. But looking into your energy, it has literally forced me to teach you almost whatever details I can provide. And the reason is, we have only covered up till shear force diagram, even few more shear force diagrams are left. So tomorrow, same time, 6 p.m. to 9 p.m., we will be continuing with the session, and if required, we can conduct one more session of strength of material, but let's see tomorrow how much we can finish. Tomorrow, my main target will be covering shear force and bending moment diagram, then principal stresses and strain, and the third topic will be deflection. In between, if I'll get some time, we will see bending and shear stresses, and we will also talk about torsion of shafts and the other things. Okay. But for tomorrow, these three things will be on my priority. My dear, thank you so much. I have literally enjoyed today's session like anything. Looking into your energy, looking into your calculation speed, fantastic. Just keep your energies high. And I'm expecting you tomorrow also from 6 p.m. onwards. We will start with this fantastic session of gate score booster of strength of material, and I'm expecting full attendance. If you have literally enjoyed this session, please don't forget to share with your friends. Please share your experience learning with IMS Gate Academy, learning with Prateek sir. Thank you so much, my dear, for getting here, staying here in the session and answering properly. I literally enjoyed today. Thank you so much. Before leaving, I just like to want to make few certain announcements. It is related to our programs. So first of all, my dear, if you haven't joined our Telegram group, kindly join our Telegram group. The link is provided to you in the description box. You will get the lecture PDF in our Telegram group itself. Second thing, we at IMS Gate Academy, we provide you with 800 hours of live teaching with interaction, with doubt solving. Along with that, we provide you with theory and exercise book containing 4,000 practice questions, well versed in level 1, level 2 and level 3. We provide you with 33 years of gate question bank in which we have provided detailed solution, alternate solution, key points with chapter overview. We provide you with 12 personalized one-to-one mentoring sessions, and along with that, we provide you with India's largest test series. Thank you so much for this session. Best as always. Thank you so much, Saundarya. Thank you so much. From this year onwards, we have launched this course which is called as Test Series Plus, where we are providing with 20% discount. If you want to enjoy this Test Series Plus course, right, the Google form link is given in the description box. You can just fill the form and you can connect with our education advisory team, and they will guide you what all features they will provide. Basically, we are providing you with the test series along with the gate question bank of maths and technical subject and aptitude. Okay. So I'm just expecting you, all of you, tomorrow, same time, 6 p.m. onwards, till the time we can enjoy the sessions. So tomorrow we can also extend the session if required. But thank you so much, my dear students, for today. I'll see you tomorrow definitely at same time, same place. Till then, please take care and have a great night ahead. Thank you so much.